In 1980, NASA designed a machine that could build copies of itself. Land one on the moon, and you would never have to launch another. They costed it, they engineered it, they said it need no new technology. 46 years later, it does not exist. And the reason why is sitting in a drop of pond water. This is the story of self-replication. Why it would change everything. Why the smartest engineering organization on Earth couldn't pull it off. And how a bacterium solved the problem billions of years before we thought of it. The sun puts out more energy every second than our civilization has in its history. Almost all of what is goes from radiating into empty space. In Biked. Freeman 2016. Arguing that goes now owns a sufficiently advanced efficient and star's output that we might not detect one by the infrared glow it gave off. A solid shell, the version that ended up in science fiction, doesn't work. It couldn't hold itself together, but a swarm could. Millions of thin mirror satellites in orbit around the sun, each one simple, cheap, and individually unremarkable. Together, they would be the most powerful machine ever built. And here is the problem that has stopped every version of this idea. To build a swarm, you need millions of satellites. At Earth's gravity and Earth's launch costs is not expensive. It is arithmetically impossible. Unless you don't launch them. Unless you send one machine and it makes the rest. That is not a thought experiment. Someone drew up the plans. There's a scale for this. In 1964, the astronomer Nikolai Kardashev ranked civilizations by the energy they command. A Type 1 controls all the energy of its planet. A Type 2 captures the entire output of its star, which is exactly what a Dyson swarm is. A Type 3 harnesses a whole galaxy. Where are we? Carl Sagan did the math. Humanity sits at about 0.73. We are not even a Type 1. We use roughly 18 trillion watts, 1,000 times short of controlling our own planet, and 1 trillion times short of our star. The swarm isn't an upgrade, it's a different category of existence. And here's what makes self-replication such a dangerous idea. It doesn't stop at the sun. The same machine that builds a swarm could build a ship, one that crosses to the next star and builds copies of itself there. These are called von Neumann probes, after the same mathematician. The physicist Frank Tipler calculated that a civilization using them could colonize the entire galaxy in about 300 million years. Carl Sagan ran the exponential version and got a number that's hard to hold in your head. A single self-replicating probe, doubling as it spreads, could convert the entire mass of the galaxy into copies of itself in 2 million years. 2 million out of 13 billion. Which is why some scientists ask an uncomfortable question. If self-replication is that easy, and the galaxy is that old, where is everyone? NASA and the American Society for Engineering Education put 15 NASA engineers and 18 university researchers in a room at Santa Clara for 10 weeks. What came out was a 400-page pages of it described a single idea, a self-replicating factory on the surface of the moon. The design was specific. You land a seed, 100 tons of machinery, roughly 4 for Apollo missions worth of cargo. After that, nothing else comes from Earth. The seed strip mines lunar regolith. It processes the ore, separating metals, refractories, volatiles. It casts basalt and lays them down as roads. Using machines, a team of 5 paving robots. It assembles them and inspects, builds a second factory, which will build forward. Once a small number of these exist, further export mass will dwindle and eventually cease. The most striking thing in the entire document, it never claims to need one invention. The design was based, in their phrase, entirely on conventional technology. Everything required already existed in 1980. So they had the plans, and they had the technology. What they didn't have was a way around one specific problem. So why did the factory die on paper when Apollo, a project just as enormous, actually flew? The difference wasn't technology. It was a customer. Apollo had one, the Cold War. A government spending 4% of its budget to beat the Soviet Union to the moon. The self-replicating factory had no such patron. It promised a payoff decades away for a mission nobody had yet decided to fly. Enormous engineering doesn't die because it's impossible. It dies because no one needs it yet. Engineers call it closure. The test is brutal in its simplicity. Break the factory down into every component it contains. If the factory cannot manufacture every single one of those components itself from raw material, then it isn't self-replicating. It's just a factory that needs deliveries. A bacterium achieves closure. It runs on roughly 10 million bits of instructions. It uses 2,000 to 4,000 distinct parts, almost all of them proteins, all assembled by the same mechanism, from materials that simply drift in by diffusion. The lunar factory needed mining, smelting, chemical separation, casting, mold making, alloying, laser machining, inspection, assembly. Thousands of distinct components, each requiring a different process. The study estimated its complexity at 100 billion to 1 trillion bits. That is roughly 100,000 times more complex than a bacterium, and about 100 times more complex than the largest software projects humans had ever completed. Nothing about it was impossible. It was simply enormous. And enormous is what kills projects that have no immediate customer. So we shelved it. And then, quietly, we started borrowing from the thing that had already solved it. At Delft in the Netherlands, a microbiologist named Hendrik Jonkers asked a smaller version of the question. Not can a machine copy itself, but can a material repair itself? His answer was to put living bacteria inside concrete. They're alkali-tolerant species from volcanic soda lakes, the only places on Earth chemically similar to the inside of concrete. Mixed in as spores along with calcium lactate, they can lie dormant for 200 years. When a crack opens, water gets in and wakes them. They consume the calcium lactate and excrete limestone, which fills the crack from the inside. The limits are real, cracks up to about 0.8 millimeters and roughly 2 months to seal. But notice what happened. We didn't engineer closure. We hired something that already had it, but the idea never fully went away. It just got smaller and quieter and real. Today, NASA has a program called MMPACT, autonomous construction on the moon, using the lunar soil itself as the raw material. In 2020, it awarded a company called Icon a $60 million contract to develop a system that 3D prints structures directly from regolith. Landing pads, roads, shelters, built on the moon from the moon with almost nothing shipped from Earth. It could fly as early as 2027. It is not a self-replicating factory. It cannot yet build a copy of itself. But it is the first real step down the exact path that 1980 report described. A machine that makes its own building material, in place, off-world. There's a pattern worth sitting with. Every time we tried to build a machine that maintains itself, we hit the same wall. The sheer number of things it must know how to make. And every time biology solved the same problem, it used one trick, over and over, on materials that came to it. Maybe that's the lesson those 1980 engineers were missing. Maybe self-replicating machines were never going to be built all at once by us. Maybe they were going to be grown, one small, self-sufficient step at a time, until a machine on the moon can finally make another. The blueprint has been public for 46 years. We're only now laying the first brick.